Hey there, awesome physics students. Let's talk about the behavior of neutral but polar objects in electricity. Now, I mentioned before that neutral but polar objects could still participate in electric force interactions. We're going to see how that works. The main idea here is that electric force depends on distance. That is, the electric force is bigger when two charges are closer together. All right, so let's start by thinking about, let's say we have a conducting sphere, like a conducting ball or something like that. That's a conductor. And we put it next to a positively charged rod. What's going to happen? Well, the conducting sphere has positive and negative charges inside it, and those charges are free to move. So what's going to happen is that the negative charges in this conducting sphere are going to be attracted to this positive rod, and the positive charges are going to be repelled. And so they're going to try and get away as much as possible. Now remember that the electric force depends on the distance. So there's going to be an attractive force here between the negative charges in the positive rod, and there's going to be a repulsive force between the positive charges and the positive rod. Which one wins? Well, because the negative charges are closer to the positive rod, they will win, because that means their attractive force will be bigger than the repulsive force from the positive charges over here. And so this will attract this way. And of course, because of Newton's third law, this will also attract with an equal and opposite force. Now, this behavior or this interaction is extremely important for understanding how polar but neutral molecules interact with other molecules. So let's say you have a molecule that is polar, and think of water as your typical example because that is the most common and most important polar molecule here. And it's in an animal's body, and it is attracted to, or it's interacting with a positive ion. What's going to happen here is, of course, this is going to be attracted because of the negative charge, and it's going to be repelled because of the positive charge. But of course, in the way I've drawn this, the negative charge is closer, and that is going to feel a bigger force, bigger attractive force than this repulsive charge, and so it's going to attract. These two are going to attract. Now you might say, well, yeah, you just drew it that way. Let's draw it this way so that it's positive charges on this side, and it's next to the positive ion here. Now this is going to repel, but what happens in practice is that this one will feel a repulsive force. This one will feel an attractive force. And what happens is that the molecule will flip over, and then pretty soon because the positive charge is trying to get away, and it will flip over and quickly become in this configuration. And now the negative charge is closer to the positive charge, and it will again feel an attractive force. Okay, and you'll always get some kind of imbalance like this where they're not totally aligned perfectly, so that except for in very, very rare circumstances. And so there'll always be some tilt here, except for in very rare circumstances. And so you can always get them to flip over and attract each other like this, okay? And so this is how water molecules participate in electrical force interactions with ions and even each other, right? That's what the so-called hydrogen bonding is all about, is that you have a positive charge, a polar molecule, and it's going to be attracted to another water molecule like that. And they make and break those bonds many times per picosecond, which is a millionth of a second. So these bonds are occurring quickly and breaking, and they're all due to the electric force.